So for example, this resource request actually gives you access to more than just node 1853. It could actually be a separate node which has 16 CPUs and 64 gigabytes of RAM. The catch is that something that you execute here, for example, ls, is not magically being mirrored in the other node. All right, you need to write, or your programs need to be able to take advantage of distributed nodes. And the most popular way of doing that is using something called MPI. How many of you have heard of MPI? All right. So there's two kinds of parallelism that you can extract from the Palmetto. You can utilize the multiple CPU cores within a certain node, and a lot of commercial software and a lot of open source software can be configured to do this very easily. Okay, so that's one kind of parallelism that you can use, is the multiple cores within a node. And then you can also leverage doing work across different nodes at the same time. And generally you want to use MPI to do that. And that's another class in itself. But you want to use MPI to take advantage of different nodes only when these nodes need to talk to each other in some way. If the task that you're doing is what we call embarrassingly parallel, or it has many different subtasks that can each be done independently without having to talk to each other, then you don't have to learn about any of this stuff. And so your research problems fall generally in one category or the other. Okay, either you have many small tasks that can each be done independently and they don't need to interact with each other at all, and that's what we call embarrassingly parallel. Or you just have a very large problem that doesn't fit on your machine, you need to move it to the Palmetto, and you want many cores working on that problem together and somehow communicating with each other. And generally, things that fall into this second category are numerical simulations of physical systems. Like for example, if you're simulating fluid flow or doing some kind of molecular dynamics. But there are a lot of problems that fall into the first category of many small tasks that just need to be done independently. And so when we look at Nelly's problem here, which category do you think this one falls into? Do we have the embarrassingly parallel, or do we have the not so embarrassingly parallel? We have an embarrassingly parallel task. We have 10,000 files that we want to analyze using some Python program that we've written. But each of these analyses can be done entirely independent of each other, right? These things don't need to talk to each other in any way. And so we'll be looking at a problem that's embarrassingly parallel today. And dealing with harder parallel programs is the topic of another workshop in itself. All right. Okay, so let's go ahead and get started here. We're logged into a compute node, and we want to start running some code here. Okay, so let's look at Nelly's files. Let's go into data HPC / North Pacific Gyre / 2012-07-03. This, by the way, is where Nelly's input or files from the assay machine actually live. Okay, they're in this directory here. So let's go in there and have a look. We see a bunch of files that are all called NE, followed by some kind of identifier, and then finally the A or B or Z.txt. And so NE just stands for Nelly Nemo. And then there's some kind of identifier for the sample itself. And then A, B, or C just refers to where geographically, which one of the 3 sites that Nelly collected samples from that particular text file stands for. And so you'll remember that each of our text files looks like this. Head, remember, prints the first 10 lines of a file. And so all of our files just look like this. And we mentioned that we have a program to analyze, sorry about this, let's see. Just give me a second here while I figure this out. Okay. So we mentioned that, sorry about this. Wow. Okay. So here's all our text files. And we mentioned we have a program to analyze each one of these sample files. Can you tell me what the name of that program was? So we have a program here that's used to analyze each of these text files. And we said, what was that program called? Stats.py. It's a Python script, and you can have a look at it. Python scripts are just text files in themselves, and it's just a bunch of Python that you may or may not understand, but that's okay. We have a Python script to analyze each file, and in order to use it, here's what we have to do. We have to say Python followed by the name of the script that we're trying to execute, the name of an input file. And that's it. That's all we need to specify for stats.py to run its analysis. Okay, and this is not going to work. Okay, and so we get some kind of error, but I'll tell you it has to do with the version of Python that we're running. Okay, or where that Python is coming from. And here we have to get into a fairly long and detailed conversation about Unix and how it works. And Palmetto and how it works. So when we type in the word Python, and you can hit enter, that's just going to open up the Python interpreter. You see that we run Python 2.6.6, okay, and exit or Control D will take you out of here. Control D, remember, will take you out of Python. But you have to understand where Linux is looking for this Python program. And to do that, you can type in which Python. Okay? So when you type in which Python, it tells you where Unix looks for the Python program to start executing it. And in this case, it's this location /user/bin/Python. That's where it is. So for example, Python is really just the same as typing in the full path to that program. So typing in user bin Python does exactly the same thing. And Control D will exit from here. Okay, but if it lives in user bin Python, then how does Unix know to find it when we just type in its name like this? Like why? How does Unix know where to look for this program Python? The answer is that there is a set of directories or locations that Unix looks for when you type in the name of a program. For example, when you type in ls, it doesn't magically know what ls is or where the ls program lives. In fact, ls lives in /bin/ls. So how does it know where to find the ls program? The answer is that there is a set of locations, and those set of locations is given by a variable called path, like that. So when you echo the path, and you'll see maybe something a little bit more different, you get a list of locations where Unix will look for your programs. Okay, and one of these has to be /user/bin. The other one will have to be /bin. You'll see it somewhere here.